Hi everyone. This is Dr. S. Venkateswarlu, working as a professor of ECE at the Institute of Aeronautical Engineering, Hyderabad. Today we will discussing about active filters, and these active filters uh, major agenda is classification of filters, first order low pass filter and high pass filters. These are the major topics, contents. So filters. Now we are ready to enter the term filter. The filters are electronic circuits that allow for what you call certain frequency components, and or we can say it is a reject some other. Here we might have come across filters in network theory tutorial with reference to that, verifying these all filters, how they are justifying filters or electronic circuits that allows the certain frequency components or reject some others. They are using their passive and the electric circuits or network that consist of the passive elements, like that are passive elements or passive electronics, what you call passive components, like a resistor, the one is capacitor, and or we can consider it an inductor. So in the filters, why they are using the filter or electronic circuits? Because of they are using that passive component or passive elements like resistor, capacitor, and inductor. And an active filter, an electronic filter, is often a frequency selective circuit. That passes a specified band of frequencies and blocks or attenuates signals of frequencies. Like outside this band, filters may be classified in a number of ways. Okay, so one is analog or digital. If they are using this, the analog or digital, if you are using the analog filter, they are using the passive element or passive component. If you are considering that all digital filter, using its active component or active element. Okay, so in audio, AF or radio frequency or audio frequencies, they are using this type of filters like analog or digital or what you call passive or active. Okay, using the components. Analog filters are designed to process analog signals. Analog signals, already we know that it is a continuous time signal. We know that already. Okay, so which digital filters process analog signal using the digital technique. It is all depending on the type of elements used in their what you call construction, maybe that circuit diagram. Filters may be classified as passive or active. So within this, using this passive or active elements, the elements used in the passive filters are resistor, capacitor, and inductors. If you are using the capacitor and resistors and inductors, there is a lot of demerits in inductors. There is a big problem with inductors. We will see that. In active filters, on the other hand, employ the transistors or op-amp. There is a possibility for active filters using these all elements or components, or the other hand, maybe it employ the transistors like its active component. Okay, maybe we can consider it operational amplifier or op-amp. Op-amp additions to the transistor and capacitor. Op-amp, if you are using the operational amplifier in additions to the resistors and capacitors. Okay, so the type of elements used dictates that operating frequency range of the filter. So within this, the analog filters are designed to process analog signal, while digital filter process analog signals using the digital techniques. That means by using the solar, we require by using the active filters, maybe by using the transistors, or maybe operational amplifier. In addition with this, sometimes they are using the resistor and capacitors. Okay, so like this, yeah, using this all are the type, we are right to enter the types of active filters. So how it is formed the active filters? By using what you call using the transistor, or maybe a what you call operational amplifier, with the help of this what you call resistor and capacitor, maybe internal or external. In active filters are the electronic circuits, we know that, which consist of active elements like operational amplifier, along with the passive elements like resistor and capacitor. So active filters are mainly classified into the following the four types based on the band of frequencies that they are allowing and or rejecting. So that means it allows only low frequency components. Sometimes it opposes the low frequency components, or sometimes it allows the only high frequency components. It opposes the low frequency components. Based on this, active filters are mainly classified into the following the four types based on the band of frequencies that they are following and particular or maybe rejecting. So active low pass filter and active high pass filter. After that, active band pass filter, and fourth one is active band stop filter. This is the four types based on the band of frequencies that they are allowing and rejecting. So an active filter offer the following advantages for the passive filter. Okay, what is that? This means gain and frequency adjustment flexibility. This is the major merit, since the operational amplifier capable of providing a gain. Yeah, the input signal is not attenuated as it is in the passive filter. Okay, and in addition, the active filter is easier to tune or adjust. This is the major advantages, major merits. An active filter offers the following advantages for the passive filter. Okay, so no loading problem. Sometimes we are right to observe the no loading problem because of the high input resistance. Yeah, due to this high input resistance, where Ri is high. Okay, within this high input resistance and low output resistance. If it is output resistance is low, resistance is low of the in operational amplifier, the active filter does not cause loading of this source or load. So that means this is the no loading problem because of the high input resistance and low output resistance of the operational amplifier. The active filter does not cause loading of the source or load. Okay. Yeah, other thing is using this cost. Typically, active filters are more economical than passive filters. So we know that all based on the cost. Due to this, all other parameters like reliability and other parameters based. This is because of the variety of cheaper op amps and the absence of inductors, because of there is a demerits while we are using that inductors. Yeah, the most commonly used filters are this. One is low pass filter and high pass filter, band pass filter, and band rejection filter. Okay, so sometimes they are ready to use the all pass filters. Okay, now coming to the active low pass filter. So in active low pass filter, using this operational amplifier, that is using this simple circuit diagram op amp. Yeah, that inverting terminal is connected with R1. R1 is connected to the ground. Non-inverting terminal is connected with the RA, with the CA, the capacitor and resistor is connected. The CA is connected to the ground, where RA is given to the VN. Okay, that inverting terminal is connected to the RF, feedback resistor is connected with the ground, what you call that output voltage V0. Like this, this is the simple circuit diagram related to the active low pass filter. that active low pass filter, by using this all active components, like there is a possibility by using the transistor or maybe operational amplifier. Here we are using that operational amplifier. So if an active filters allows passes are only low frequency components, so and rejects the blocks all other high frequency components. That means using the simple circuit diagram, it allows only low frequency components, high frequency components are opposites. So then it is called as an active low pass filter using operational amplifier. Yeah, the circuit diagram of an active low pass filter is shown in figure. We know that the electric network which is connected to the non-inverting terminal of an what you call op amp is a passive low pass filter. Okay, because of they are using that what you call capacitor and resistor. So the input of a non-inverting terminal, okay, of an op amp is the output of the passive low pass filter. Okay, observe that the above this simple circuit diagram resembles that a non-inverting amplifier. It is having the what you call output of a passive low pass filter as an input to the what you call the non-inverting terminal of an op amp. Hence, it is produced an output that is followed by V naught. Okay, which is what you call 1 plus RF by R1 times the input present at the non-inverting terminal. So we can choose the value of RF and R1 because of here it is all available R1 and RF. Okay, so which is we can choose that the values of RF and R1 suitable in order to obtain the desired gain at the output. Okay, suppose if we consider the resistance values, so if resistance values are inverting terminal is connected to the R1, non-inverting terminal is connected to the RA. Within this desired gain in the output, suppose if we consider the resistance values of RF and R1, like here it is at feedback resistor that RF is available, and RF and R1 as 0 ohms and infinite ohms. Then the above circuit, consider the simple circuit diagram. Okay, we'll produce the what you call unit gain low pass filter output. Okay, if you are this is all depending upon free feedback resistor and R1 as 0 ohms and infinity ohms, then the above circuit will produce a what you call unity gain low pass filter output. Okay, yeah, low pass filter output. Yeah, here it is. The gain is, we know that all gain with reference to previous circuit diagram. The gain is output voltage by Vin. So here it is. It allows only what you call low frequency components. It opposes what you call high frequency components. Here it is. It is considered the pass band and stop band. There is ideal responses also available here. This is the ideal responses. This it allows it to the pass band. This is stop band. So we are drawing that simple that gain versus that frequency. The gain is output voltage by Vin with reference to previous circuit diagram. So within this active, this is related only what you call active filters, low pass filter output. Coming to this active filter, active high pass filter. So here it is similar to the previous circuit diagram, but here it is inverting terminal is connected to the R1, R1 is connected to the ground. Yeah, this circuit, isn't it? That non-inverting terminal is connected with the capacitor and what you call resistor. The capacitor is connected with the Vin. If active filters allows only high frequency components and rejects all other low frequency components. That means by using this high pass filter, it allows only high frequency components. It rejects low frequency components. Then it is called an active high pass filter using operation amplifier. The circuit diagram of an active high pass filter is shown in following the figure. We know that the electric circuit which is connected to the non-inverting terminal of an op-amp is a passive high pass filter. So the input of an non-inverting terminal, input of the non-inverting terminal of op-amp is the output of the passive high pass filter. Now, so the circuit diagram resembles the non-inverting amplifier. It is having the output of a passive high pass filter as an input, and input to the non-inverting terminal of op-amp. Hence, it is produced produces an output that is going to be what we call V naught, which is 1 plus RF by R1 times the input resistance at its non-inverting terminal. Yeah, we can choose this value of RF and R1 suitably in order to obtain desired gain at the output. Suppose if we consider the resistance value of RF, feedback resistor, and input resistor R1 as 0 ohms and infinity ohms, then the above circuit will produce a unit gain high pass filter output. Okay, this is the simple circuit diagram. After this, you have to consider that active high pass filter. Yeah, active high pass filter output response, here it is. Yeah, here the gain versus the frequency. Yeah, here it is pass band. It allows only high frequency components, low frequency components are rejected, that is stop band and pass band. Based on this, active high pass filter output response will be like this. Okay, next coming to the active band pass filter. Here it is given to the, if an active filter allows only one band of frequencies, so then it is called as an active band pass filter. So how we are agreeing this one, if an active filter allows or maybe passes only one band of frequencies, so then it is called as an active band pass filter by with the help of this simple circuit diagram. Here it is just now we have verified that all two circuits diagrams are available. Concentrated on this circuit diagram. That is high pass and low pass, both are available here. Yeah, that high pass filter is output response is connected with this inverting, non-inverting terminal. Okay, so like this, in general, this frequency band lies between the low frequency range and high frequency range. So active band pass filter rejects frequency components. So the circuit diagram of an active band pass filter is shown in the following. So figure observe that there are two parts in the circuit diagram of active band pass filter. The first part is an active high pass filter. Consider this one. This part is already we have seen this one. High pass. The first part is an active high pass filter, while the second part is an. What they say? This is the first part, and this is the second part. The second part, while the second part is an active low pass filter. That means this is the high pass filter using the operational amplifier. This one low pass filter with the help of what you call op-amp. Okay, so the output of the active high pass filter is applied as an input of the active low pass filter as per this circuit diagram. Okay, so that means both active high pass filter and active low pass filters are cascaded in order to obtain the output in such a way that it contains only a particular band of frequencies. So the active high pass filter, which is present at the first stage, allows the frequencies that are greater than the low cutoff frequency of the active band pass filter. So as per this circuit diagram, the output of the active high pass filter is applied to an input of the active low pass filter. Due to this, the active high pass filter, which is present at the first stage, allows the frequencies that are greater than the lower cutoff frequency of the active band pass filter. So we have to choose the value of RB and CB suitably. Okay, that means based on this all resistor and capacitor to obtain the desired low cutoff frequency of the active band pass filter. So similarly, the active low pass filter, which is present at the second stage, allows the frequencies that are the what you call smaller than the higher cutoff frequency of the active band pass filter. So we have to choose the value of RA and CA suitably in order to, so similarly like RB and CB, so to obtain the desired high cutoff frequency of the what you call active band pass filter. Okay, hence the circuit is in the diagram discussed above will produce as per the previous circuit diagram. So an active band pass filter output, okay, like this. So the output response is frequency versus the gain. We know that gain is output voltage by input voltage versus that frequency. Okay, so low frequency components are opposites, and what you call using this all high pass low pass filter, it allows only low frequency components. It opposes high frequency components because of your high pass filter. It allows only high frequency components. It opposes low frequency components. With the help of this, we are FL and FC and FH. So now it is stop band and pass band, where if it is stop band, based on this all things, ideal response in practical response easily can observe using this active band pass filter output response based on frequency versus that gain. Next, coming to this active band stop filter. So if an active filter rejects or maybe blocks a particular band of frequencies, then it is called as an active band stop filter. Okay, so in general, this frequency band lies between the low frequency range and high frequency range. Okay, so active band stop allows the passes both low and high frequency components. So the block diagram of an active band pass band stop filter, as per the circuit diagram, here it is. Input signal is here. So that input signal is given to the active low pass filter and active high pass filter. Output of this active low pass filter is given to the summing amplifier. Output of the active high pass filter is given to the summing amplifier. Finally, we will expect that output signal. Due to this, if an active filter rejects blocks as a particular band of frequencies, so active band pass filter allows both low and high frequency components. So observe that this block diagram, as with the previous diagram of an active band pass band stop filter, consists of two blocks. In its first stage, an active low pass filter and an active high pass filter. So the outputs of these two blocks are applied as input to the block that is represented in the second stage. So the summing amplifier produces an output. Okay, this all depending upon what you call active band stop. It consists of two stages. First stage is active low pass filter and the second stage is active high pass filter. Depending upon this active low pass filter and active high pass filter, the outputs of these two blocks are applied as input to the block at the present the second stage. So the summing amplifier produces an output. Yeah, which is the amplified version of the sum of the outputs of the active low pass filter and the active high pass filters. Therefore, the output of the above block diagram will be the output of an active band stop. So when we choose this cutoff frequency of the low pass filter to be smaller than cutoff frequency of a high pass filter. So the circuit diagram of an active band pass filter is already we have seen that previous diagram with reference to that. So the following the diagrams are what you call figures will be estimated is can write that interpretation using now it is low pass filter. Now it is justifying the high pass filter to be smaller than the cutoff frequency and so on. For that purpose, we require this simple block diagram here. So we have already seen that the diagram of the active low pass filter and active high pass filter and summing up. Observe that we got the above circuit diagram of active band stop filter by replacing blocks, which is that what you call respective circuit diagram, the block diagram of active band stop filter. So here in this case, active filter, first order low pass Butterworth filter. Yeah, within this, in the first order low pass Butterworth filter that uses an RC network for filtering. Okay, note that the operational amplifier is used in non-inverting configuration. If you have the inverting configuration, the parameter will change. That's why the op amp is used in the non-inverting configuration. Hence, it does not load and down the RC network. Within this, resistor R1 and RF determine the gain of the filter. Okay, the gain of the filter according to the voltage divider rule, the voltage at the non-inverting terminal where particular across the capacitor is, so where V1 is equal to minus jXC by R minus jXC into Vin, where J already we know that for this J value, okay, this J value is equal to square root of minus 1 and minus jXC is equal to 1 by, here it is 1 by J2 pi Fc, where V1 is equal to Vin by 1 plus J2 pi F RC. The output voltage is equal to 1 plus RF by the feedback resistor by R1 into V1. Okay, so like this easily can interpret that output response is where output voltage is equal to 1 plus RF by feedback resistor by input resistor R1 into Vin by 1 plus J2 pi F RC. So output voltage by input voltage is equal to where the gain of the filter as function of the frequency, where AF is equal to 1 plus RF by R1, pass band gain of the filter, where F is, we know that one, frequency of the input signal, where FH is equal to 1 by 2 pi R into C, high cutoff frequency of the filter. While we are using this all mathematical notation, how it is coming from this all. So from this here, yeah, using the operational amplifier, using the simple circuit diagram based on this, typically they are using this R1 and R2 and what you call RF. Using this all typical value, we will try to verify that Vin is applied. After that, we try to verify that output response of this with reference to that frequency versus the voltage gain. Okay, so you can verify that stop band and pass band. So that typically it is observed that by calculating that FH, where FH is equal to high cutoff frequency of the filter. Okay, and that high cutoff frequency of the filter, it is measured with the help of this FH is equal to 1 by 2 pi R into C. Okay, so next output voltage by input voltage. So it is also equal to AF by square root of 1 plus F by FH whole square, where pi is minus tan inverse of F by FH. Okay, so like at very low frequencies, that is F less than FH, where output voltage is equal to input voltage, it is approximately equal to what we call AF. Next condition at F equal to FH, output voltage by input voltage, AF by square root of 2, it's around what we call, here graphically it is mentioned, this 0.707 AF. Third one is at F greater than FH, output voltage by input voltage less than AF. So that is related to the first order. Coming to the second order low pass Butterworth filter, the stop band response having a 40 decibels per decade roll off is obtained with the second order low pass filter. That means we require the stop band response, and second order low pass filter will be at first order low pass filter can be converted into a second order type simply by using an additional RC network. How we are adding that RC network in additionally with help of this. Okay, so additionally it is added R and C. So say this is going to be what you call second order low pass Butterworth filter. Okay, that is the frequency response with the frequency versus voltage gain. Okay, with reference to this circuit diagram, second order low pass Butterworth filter, it is drawn in as per the circuit. Stop band response having what you call 40 decibel per decade roll off is obtained with the second order low pass filter. Due to this simple circuit diagram, a first order low pass filter can be converted into a second order type simply by using an additional R and C. Okay, as per the circuit diagram. So high cutoff frequency FH is determined by R2, C2, R3 and C3. Like here, R2, C2, what do you call? So using the simple circuit diagram. Okay, that R1, R2 and R2, C2, R3 and C3 as follows. So further, for the second order low pass Butterworth filter response, the voltage gain magnitude equation is where FH is equal to 1 by 2 pi square root of R2 into R3, C2 and C3. This is the high cutoff frequency. FH is determined by R2, C2, R3 and C3 as follows. It is therefore the Fs is equal to 1 by 2 pi square root of R2, R3, C2 and C3. Further, for second order low pass Butterworth response, the voltage gain magnitude equation is like this: output voltage by input voltage is equal to what you call AF by square root of 1 plus F by FH whole power 4, where F is equal to 1 plus RF by R1. It is nothing but where AF, what you call pass band gain of the filter. From this case, where F, we know that one, where F is frequency of the input signal, in terms of that Fs is equal to 1 by 2 pi into square root of R2. We know that one, square root of R2, R3, C2 and C3. It is followed by high frequency, high cutoff frequency. Yeah, in coming to this first order high pass Butterworth filter. So that means high pass filter are often formed simply by interchanging so frequency determining the resistor and capacitor in low pass filters. So that is the first order high pass filter is formed from a first order low pass type by interchanging components R and C. So here it is. So as per this, you can consider that all inverting terminal is connected with R1 and R1 and RF is connected to output response V0 with the load resistor R. Okay, V is connected and VCC and non-inverting terms connected to the R. It is okay with this capacitor and capacitor connected with Vin. Okay, this is the first order high pass Butterworth filter. So using the simple circuit diagram, you will expect this output response like frequency response based on frequency versus voltage gain. Okay, so for this simple circuit diagram, we try to calculate the output voltage where V0 is equal to 1 plus RF by R1 into J2 pi F on RC by 1 plus J 2 pi F RC into Vn. Where output, we know that output voltage, but we know that all input voltage also, where output voltage by input voltage is equal to, right, to calculate, where it is AF into J of F by FL by 1 plus J of F by FL. So where AF is 1 plus RF by R1 is equal to pass band gain of the filter. You know that FL value, this is the low cutoff frequency. So within this, So finally that output voltage, the gain is calculated, output voltage by input voltage. So based on this voltage gain and the frequency, easily can calculate that, measure that output response a given filter. Okay, so like this. Next, coming to the second order high pass Butterworth filter, as in the case of the first order filter, a second order high pass filter can be formed. So from a second order low pass filter, simply by interchanging the frequency determining the resistor and capacitor. After that, we are right to consider the second order high pass Butterworth filter. Okay, second order high pass filter, based on this simple circuit diagram, that inverting terminal is connected to the R1 with this RF connected to the output voltage. So inverting and non-inverting terminals connected to the R3, capacitor C3, and R2. RT is connected with the what you call the output V0. So where C2 is connected to the C2, C3 is C2, and C2 is connected to the Vn. So after that load resistor RL is also available, connected with the V0, second order. After that, we will consider this second order high pass Butterworth filter. As in the case of first order circuit, the second order high pass filter can be formed from the second order low pass filter simply by interchanging the frequency, determining resistors and capacitors. So based on this, we have to follow this simple circuit diagram. Based on the circuit diagram, usually can verify the output response with the gain, voltage gain by versus with the frequency. So, but we have to calculate by using the simple circuit diagram. We can write to calculate the voltage gain, where V0 by Vn of that frequencies. Usually can verify that response, frequency response of what you call it's the frequency response of the given second order high pass Butterworth filter. Okay, within this, we write to calculate the output voltage by Vn is equal to AF by 1 plus FL by F power 4. So where AF is equal to 1.586. This is the pass band gain for the second order Butterworth responses. Yeah, in numerically, how they are choosing AF is 1.586. We will see that the problematic point of view. We will verify that. Where F is the frequency of the given input signal. So where FL, we know that lower cutoff frequency, and since second order low pass and high pass filter are the same circuit, expect that the position of the resistors and capacitors are interchanged. Yeah, easily can observe that both of that first order and second order low pass and high pass filters are the same circuit, except that the positions of the resistor and capacitors are interchanged. The design and the frequency scaling procedures for the high pass filter are the same as those for the low pass filter. So you can observe both the circuit diagram using this all inverting and non-inverting terms connected with all the R and C, resistor and capacitor. Position of the resistor and capacitors are, if it is changed or interchanged or not. Yeah, if it is interchanged, the design and the frequency scaling procedures for the high pass filter are the same as those for the low pass filter. Okay, next coming to the band pass filter. The band pass filter has a pass band between two cutoff frequencies, FH and FL. That means high frequency and low frequency, such that FH is greater than FL. Any input frequency outside this pass band is attenuated. So basically, there are two types of the band pass filter. You know that one. One is wide band pass and narrow band pass. With reference, the pass band filter has the pass band, what you call, between the cutoff frequencies FH and FL. Yeah, that condition should be FH greater than FL. So there are two types of band pass filter: wide band pass and narrow band pass, where it is Q is equal to FC by the bandwidth is equal to FC by high frequency minus low frequency. Wide band pass filter, the center frequency FC can be defined as FC is equal to square root of what you call high frequency into low frequency, where FH is the high cutoff frequency and FL is low cutoff frequency of the wideband pass filter in terms of the hydration. So in a narrowband pass filter, the output voltage peaks at the center frequency. Like this, the circuit diagrams are available. Here it is the first order high pass section, first order low pass section. In first order high pass section, here the inverting terminal is connected to the R1 with the RF with the output voltage V, and non-inverting terminal is connected to the R, the capacitor we connect to the V in. The output of the first order high pass filter section output is given to that inverting non-inverting terminal of first order low pass filter. Inverting terminal is connected to the R1 dash and RF dash connected with this V0. We are having that load resistor, or it is connected with minus VE, minus 15 volts plus VCC plus 15 volts. But here it is specified in first order low pass filter, FH is given 2 kilohertz. Here it is first order high pass filter, the FL is equal to 200 hertz. Due to this all our frequency response, the response is right to calculate frequency response, where if it is A1 and A2 dual op amp, like they are using the A1 op amp and A2 op amp, they are using the 1458 353 ICs. That's the frequency response, frequency versus the gain. Okay, so with this wide band pass filter, a wide band pass filter can be formed by simply what you call cascading high pass as per the circuit diagram. Due to this, depending upon first order high pass section as well as first order low pass section, so wide band pass filter, a wide band pass filter can be formed by simply cascading high pass and low pass sections, and is generally the choice for what you call simplicity of the design and performance. This is the based on the design is in terms of the first order high pass filter and first order low pass filter. Consider these two sections. We can consider this is the what you call. So we have wide band pass filter. With reference to this, we will expect the output response, because of they are given that the first order high pass filter section input is given in the right side, what you call output section, first order low pass section or filter, we not try to calculate its frequency response. That means it is all are depending upon A1 and A2 dual op amp. They are using what you call 1.4. Yeah, here they are using the 1458. Here they are using what you call in terms of this 353. Okay, is the frequency response, frequency versus the gain, stop band, and what you call stop band versus pass band. So for this case, output voltage by input voltage, mathematical interpretation, right, to measure the mathematically output voltage by input voltage with the AFT of F by FL by square root of 1 plus F by FL square 1 plus F by FH square, where AFT is the total passband gain. Okay, where what you call this AFT, so where this AFT is followed by what you call total passband gain. Frequency, we know that the frequency of the input signal, and FL we know that low cutoff frequency, and FH is high cutoff frequencies. So now coming to the narrow band pass band filter. The narrow band pass filter using the multiple feedback is shown. Multiple feedback, how? As shown in figure. The first uses only one op amp compared to the all the filters like low pass, high pass, and band pass, and so on. So as per this, what we call filter is unique. In the following the respects, it has two feedback paths, hence the name multiple feedback filter. So the op-amp is used in the inverting mode. Okay, so for this case, okay, here it is mentioned that multiple feedback narrowband pass filter. Now it is here. The inverting terminal is connected to the vertical C1 and R3. Okay, here as per this, so where compared to all the filters, this here it has two feedback paths, hence the name multiple feedback filter. The op-amp is used in the inverting mode. Okay, so where AF is the gain, that the frequency is given by what we call like multiple feedback narrowband pass filter. This is the output response where you are using this multiple feedback narrowband pass filter. Okay, so it's a frequency response, frequency versus what we call the gain, output voltage by Vn. So the circuit components are determined from the following the relationship to simplify the design calculation. We are using the typical value, easily can ready to verify that all frequency response with reference to that frequency versus that gain. So choose that all C1 is equal to C2 is equal to Cu. We know that one. So where R1 is, it is ready to calculate Q by 2 pi Fc into AF, where R2 is equal to Q by 2 pi Fc, C of 2Q square minus F, where F is the gain at Fc given by A3, R3 is equal to Q by F into Fc into C. Okay, that AF is, but here we don't know that AF, where AF is equal to R3 by, where is that R3 here, that feedback resistor, where R3, where R3 by 2 into R1, because of their multiple feedback narrowband pass filter. Due to this, we have to calculate the R1 and R2 and R3 and R4. Okay, due to that gain and as well as this typical value. Yeah, next coming to this band rejection filter. The band rejection filter is also called as band stop or band elimination filter. Yeah, in this filter, frequencies are attenuated in the stop band while they are passed out outside this band. Band reject, the filter can also be classified as wideband rejection and narrowband rejection. Wideband rejection and narrowband rejection. It is classified based on this band. The band reject, the filter can also be classified as wideband reject or maybe narrowband reject. So the gain AF aware must satisfy the condition. What is the condition? Based on the condition, right, to verify that band reject filters. Okay. So another advantage of this multiple feedback filter, this as per figure, is that it is center frequency Fc can be changed to a new frequency F-C without changing the gain or bandwidth. This is accomplished simply by changing R2 to R-2. So that, okay, so where AF is less than 2 into Q square. Okay, or maybe R, if you want to verify that R-2 R2 dash is equal to R2 into Fc by F-T by L square. Here you have to consider the wideband rejection filter. Here, how many op-amps are required here? A1, A2 and A3. So, with reference to this narrowband rejection filter. So, the narrowband rejection filter, often called as the notch filter, is commonly used for the rejection of the single frequency such as the 60 Hz power line in the frequency. So, this is the passive filter composed of two T-shaped networks. The notch output frequency, what you call, is frequency at which maximum attenuation is occurs. It is given by what you call, we have to calculate that Fn within this twin T notch filter. We have to consider this one. It is also come from active notch filter. Okay, that inverting terminal is connected to the feedback. with RL. So mm, inverting terminal is connected. Non-inverting terminal with this, what we call in terms of this 20 notch filter. Okay, T20. Check it here is R, C, and R and C with R by 2 and 2C. It is applied with this again. You will expect that our bandwidth with reference to the frequency versus the gain output voltage by input voltage frequency response of the active notch filter. You will expect this bandwidth. So that bandwidth is very high or low. Easily can verify that while we are using this type of active filters with the 20 notch filter. Maybe it using the active notch filter, we will expect that our frequency response of the what you call active notch filter. Okay, now coming to the all pass filter. As the name suggests, an all pass filter passes all frequency components of the input signal without attenuation, without any attenuation, while providing predictable phase shift or different frequency of the input signal. That's why it is the all pass filter. When signals are terminated over transmission lines, such as telephone lines, it's happened due to that different season. So they undergo change in the phase. To compensate for these phase changes, all pass filters are required. That is the greatness of all pass filter. So the all pass filters are also called as delay equalizer or phase what you call correctors. Phase correctors or maybe equalizers, delay equalizers are considered all pass filters. Okay, we are using this all circuit diagram where RF feedback resistor is equal to input resistor R1, RF is equal to R1. The output voltage V0 of the filter can be obtained by using the superposition theorem. Okay, like here, the circuit all pass filter, that inverting terminal is connected with R1, RF, and the non-inverting terminals connected with the capacitor and R. That both are connected with the Vin. Vin is applied. Finally, we will try to verify that output response. Due to this, we can consider the circuit diagram is followed by all pass filter circuit diagram. Okay. We need to calculate the output voltage, where output voltage is equal to minus V in. Why it is minus V in? But both inverting and non-inverting connected with this V in. Okay. But here, where output voltage is equal to minus V in plus minus J XC by R minus J XC into V in. So, for this output voltage is equal to V in of minus 1 plus 2 by what you call J2 pi F RC plus 1. So output voltage is by input voltage 1 minus J2 pi F RC by 1 plus J2 pi F RC. So where F is the frequency of the input signal. You know that one? Yeah, equation indicates that the amplitude of the output voltage by input voltage is unity. That is, output voltage is equal to input or throughout the useful frequency range, and the phase shift between the output voltage and V is the function of the input frequency F. The phase angle pi is given by what you call pi is equal to minus 2 into tan inverse 2 pi F into RC by 1. Like this, right? Verify phase shift between the input and output voltages. Okay, V is here. We need to verify that V in and V0, where V in is this output as V in is how this phase shift is changes here from okay phase angle versus that what you call voltages phase shift between input and output voltages. Okay, filters are circuits that are capable of the passing signals with a band of frequencies while rejecting or blocking signals of what you call frequency outside this band. Okay, yeah, this property of the filters is also called as frequency selectivity. Yeah, coming to this all passive filter built using the components such as resistor, capacitor, and inductors. Active filters employs transistor or op amp in addition to resistor and capacitor Active filters are mainly used in the communication or signal processing circuits. They are also employed in wide range of applications such as entertainment, medical electronics, etc. That is the importance of these active filters as well as the normal filter also. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.